thank you very much. It's a great pleasure to be here. It's a great conference. I have been enjoying this 2 days. So today I would like to present a joint paper with my colleagues from Erasmus University, Rotterdam, and the title is An Extended Score-Driven Dynamic Factor Model. So we contribute to the literature on dynamic factor models, and we show how to use these models to recover composite indices from the pandemic. So what is this paper about? So this paper is about dynamic factor models that have proven to be quite useful in a variety of macroeconomic and finance applications. And for example, policy institutions quite often use Kalman filter type DFMs to produce various indices to forecast inflation or nowcast GDP. So here we can see also some examples how ECB uses dynamic factor models in their work. However, COVID-19 pandemic has created some challenges for modeling of macroeconomic time series, and without any adjustment, you typically get quite different estimates from what you had before COVID, and typically you have some uninterpretable estimates and that mess up the pre-COVID fit. However, some time has passed, so we have been now 5 years since, or more 6 years after the pandemic, so there have been some, also people thought about this, how to deal with these observations. And let me guide you through how, for example, Philadelphia Fed, who construct coincident economic index and leading economics, what they have been doing with their models. So these are the 2 quotes from the Philadelphia Fed website. So for the coincident economic index, they decided to treat the entire year of 2020 as missing, so COVID never happened. And when they estimate their model, they exclude these observations. For the leading economic indices, when we started working on this project, first they temporarily decided to discontinue producing these leading economic indices. And then we were waiting when they will start finally producing them. And later on, they actually posted on their website, they will permanently discontinue producing the leading economic indices because of the COVID-19 pandemic that it had effect on the initial unemployment claims. So they said their standard approach is inappropriate and they can't proceed with this. So this will be actually also the application that I will consider in our empirical analysis. So these coincident and leading economic indices will come back later on. The New York Fed also had similar issues. They suspended first their GDP nowcast for 2 years. So this is also the quote from their website that says, the COVID-19 pandemic generated considerable uncertainty and volatility with respect to macroeconomic data. And they had decided to adjust their model, and they introduced new features. They introduced non-Gaussian innovations and time-variant volatility into their model to accommodate also these observations. And only to be able to do this, they switched from frequentist estimation that they had before COVID to Bayesian estimation that is more computationally involved. So in this paper, we introduce a new class of model, extended score-driven dynamic factor model, so ESD DFM we call it. And we introduce new features like time-variant volatility, think about Garch type, and also non-Gaussian innovations, think about students' T innovations, and we still allow it to be estimated within the frequentist maximum likelihood estimation, so no Bayesian estimation is needed here. And we also show that this model bridges the gap between parameter-driven DFMs, this is the classical DFMs that are also used by central bankers a lot, and novel class of models, score-driven DFMs. I was hoping that Sico would introduce score-driven models a bit more, so I will have to, but I will give you a bit introduction to score-driven models as well, if you are not familiar with. And in the empirical application, I show how to recover Philadelphia Fed coincident and leading economic indices, and if time permits, I will also show the same analysis for the conference board indices. All right, let me start with some illustrative examples. So first we'll talk about the single factor dynamic factor model. So typically in the dynamic factor models, you have a series that you want to model. You have n of them, and here we think about n being small, medium scale, so n is fixed. Then for this example, we have one common factor. So you summarize the dynamics of the series in a common factor. And while the factor is common, you have individual specific exposures that are summarized in the vector of loadings lambda. Then the innovations for this example are assumed to be Gaussian, they assume to be also IID, and the diagonal, the covariance matrix is assumed to be diagonal because you need somehow to disentangle what is common and what is idiosyncratic. And for simplicity and identification, I impose this restriction, but it just simplifies the formulas on the next slide, and you can think about different identification restriction. So then you need to model the factor dynamics if you want to produce later on the forecast. So one way of doing this is use parameter-driven model. So think about the state space model. So the factors are latent, and they have their own source of uncertainty, which is uncorrelated with the error term in the measurement equation. And then you specify an R1 dynamics, you put it into the Kalman filter, and that would be the Kalman filter recursion in the steady state. The key limitation of this approach is the analytical likelihood is not available once you depart from the Gaussianity and you have some non-linearities in your model. The alternative approaches that can help to circumvent these problems is to use a score-driven update. So you basically specify the factors as a function of past observations. And in this way, you can easily introduce nonlinearities. You can still use the maximum likelihood, and it will all go very nicely. And in this example, in the Gaussian case, the score would look, so you specify the likelihood, you take the logs, you take the derivative, and then the score-driven update would be given by the equation 5. So this is the score term, and this highlighted here. However, the problem is that while the filters are quite similar, then you might think of, okay, that would yield quite similar results, the likelihoods are actually, the implied model are quite different. So if we look at the conditional moments, while the first moment may be similar, the second moment definitely looks very different. And the two moments in the Gaussian case would specify the whole distribution. So in the first case, because the factors are latent, we have two terms, basically one that is coming from the uncertainty coming from the factors, and another one is coming from the idiosyncratic component. And because we assume that the covariance matrix of the innovations is diagonal, basically this sigma is diagonal, but because you have two terms, the first part is still non-diagonal covariance matrix. However, in the score-driven models, because the factors are predetermined, once you compute the covariance matrix of the data, you get that actually the first term is 0. And if you assume that your sigma matrix is diagonal, then you get that the full covariance matrix of the data, the thing that you want to model, is also diagonal matrix. So it means that you're actually not modeling the conditional covariance terms, which may contain important information. And we fix this problem. We bridge the gap between these two models by introducing a new class of model that we call extended score-driven model. Because the only thing we are doing, we have a score-driven update, and we add an additional term, and which is highlighted in blue. So this additional term is a score at time t+1. So now we're making our factors no longer predetermined at time t, but they're predetermined at time t+1. And then if we compute the first and second conditional moments, we see that we no longer have this pattern of having the covariance matrix of the data, conditional covariance matrix, to be diagonal. It's actually have a full matrix. And it's also, if you look at the formulas, they're quite similar to what we had with the conditional moments in the parameter-driven model. And what we actually show in the paper, that it's not that we are just closing this, having this moment structure that is similar. We actually show that we nest both models. In the Gaussian case, in this example, we nest the PDDFM and we nest the SDDFM. So SDDFM is quite easy to see. With the PDDFM, you need to do some derivations, and we also find out that we actually can generate every process that the PDDFM can generate. And then if you're thinking, okay, but you're introducing this t+1 innovations or t+1 observation on the right-hand side, this idea is actually very similar to the real-time Garch model that maybe some of you have seen, where you also introduce observations at time t+1, or innovations, and that bridges the observation-driven Garch type of models with parameter-driven stochastic volatility models. All right, so let me show you the general framework of extended score-driven model. So we now allow for more than one factor. We allow the loadings to be not static but dynamic, so you have a polynomial lambda now. And we also allow for temporal dependence in the innovations. We also allow the innovations to be not necessarily Gaussian, but also coming from the student t-distribution, from the general class of elliptical distributions. And we also introduce a common volatility factor, so you can model also time-varying conditional variance. So this is the observation equations. Now we look at the time-variant parameters. So the time-variant parameters follow this. The factors follow the ESD update, while the conditional variance term follows the score-driven approach. So now we have, for the factors, two terms. We have a score term, which is like a quasi-score, like typical in score-driven literature. But we have additional term that serves as an innovation and that introduces this randomness in the factors. And we always assume this S tilde to be Gaussian, and that would allow us to have a filter in a closed form, and will also allow us to have a likelihood in a closed form. So let me give you some example how this model will look like, and this will be actually the specification that we will arrive in our empirical application. So this is ESD T DFM with the Garch component. So you have a T innovations in your T distributions for your innovations. With the degree of freedom parameter nu, you also estimate these degrees of freedom parameter. We don't assume here no lags, so in empirical application that would be actually different. And now we have this innovation component in blue that we talked about. So this is S tilde. We also have a score that is looks quite similar. So this is a score from the T distribution, but we also have here an additional term, WT, that is down-weighting the effect of the large observation. So if you have UT that is very large and that the degrees of freedom parameter is small, then you would assume that this would be dampening automatically the effect of these large extreme observations. And then you also estimate these degrees of freedom parameters, so your data actually gives you an indication of how much of the dampening effect there should be. And then for the volatility, we have actually arrived at something like a Garch type of specification. So this should be also actually UT, the residuals. And then you would see that why I call it Garch, because you also have something like a squared residuals driving the dynamics of your conditional variance. All right, so this is a model, but you still have something like UT plus 1 here or YT plus 1 here. So you have FT plus 1 on the right and left-hand side, and you need somehow to work to make it work. So you actually need to develop a filter for this model. You need to filter your factors. In the score-driven models, it's quite easy because you only have a prediction step. And this separate, we will actually have two steps. It's like seq-head, prediction, and the update step. So in the prediction step, you want to forecast factors given the past information. So you condition on past information ft, and because these terms actually disappears when you condition on this past information because your errors are IAD, then you actually get a prediction as a score update. So this is quite natural. Then, after you have made this forecast, you get this new observation YT plus 1, and you want to actually update your factors. So you had this. You construct now the conditional expectation given the data at time t plus 1, and this would give you the updated factor. And this factor would be equal to the forecast plus some prediction error that you make during this period, and then something like a Kalman gain that would give you the updated factor. And then once you computed the prediction error, you computed the conditional variance, you can actually estimate all your parameters using maximum likelihood. And this is just the slide with the general likelihood function for the student t distribution of any elliptical distribution. All right, so let me show you the empirical application. As I said, in the empirical application, we focus on the Philadelphia Fed coincident and leading economic indices. So they produce the coincident economics index, which is supposed to capture the current state of the economy, which actually captures the current state of the economy. So they use Gaussian parameter-driven DFM model, and it's based on the 4 series that are listed here, and then we use as many observations as possible, so we end in December 2025. And the Philadelphia Fed treats the observations in 2020 is missing. We are trying to see what kind of model, what will be actually selected, and we will be not excluding these observations when estimating the model. So let me guide you what kind of specification is actually the data favors. So we compare the fit of the model for various legs. This is like just a part of the table from the paper. We compare parameter-driven, score-driven, and extended score-driven models. And the score-driven and extended score-driven models we consider with Gaussian and t-distributions. You can see from this table clearly that the ESDT specification that is highlighted here is selected using based on any information criteria, and also based like the likelihood improvements are just huge. It also improves upon the score-driven T model, and you see also that it's important to model this covariance term in the data. And we also find that the parameter-driven model with the Gaussian parameter-driven model and the extended score-driven model, they actually perform quite similar. So you have likelihood would be always, in this case, better in the ESD case than the parameter-driven case because we nest this model, and the information criteria will select just the most parsimonious model. Then we dive into what we want to also check whether the conditional heteroscedasticity is important and whether it improves upon the constant volatility. So here we compare the ESD Gaussian with the ESDT, and we see that the specification with the Garch component is selected. And the major improvements are coming actually from the T distribution rather than adding the conditional heteroscedasticity. So when we compare the orange highlighted cells there, we see quite big improvements, while going from the constant volatility to the Garch effects doesn't add too much. Okay, so we selected the ESDT specification with one leg in the measurement equation and one leg in the state equation with the Garch volatility. Let us look at how the factors and the volatility look like. So this is the predicted volatility factor, and we see that it mostly captures the COVID period. And it's also appears as like the model tells you that this period should be interpreted as a shock to volatility. So, and this is something in line with the literature that suggests to model this period as a shift to the volatility. But our model tells us in a flexible way that this is indeed should be the case. Then we look at the predicted factor, and we see that it captures basically the business cycle of the US economy. And we also see here that this factor is statistically different from 0 during the NBR recessions. And this is also a nice feature of our model, that we actually can produce the confidence bounds that typically the observation-driven models like score-driven models cannot do. And once we computed the predicted factor, or actually the filtered factor, we can compute the index and level by integrating everything backwards. And then if we compare to the Philadelphia Fed index, we see that they are actually quite comparable throughout the sample. And the main difference basically occurs during the COVID period, where our index doesn't go down as much as the Philadelphia Fed goes, even though they had to exclude observations during the estimation. They do not exclude it when constructing when they're filtering, but for the estimation of the parameters, they do exclude the observations. Okay. So next we recover the leading economic index. So leading economic index, it predicts the 6-month growth rate of the coincident economic index. And as I said in the introduction, the Philadelphia Fed decided to discontinue producing this index after 2020, and we show it we can revive it with our model. And we try to stay as close as possible to their methodology. They use a VRR model to construct this index. So in our case, we decided not to go with the VRR model, because then you also have a lot of problems with extreme observations during COVID. And instead, we estimate the common factor from the leading variables. So we assume a common factor structure in the leading variables. And then we model using the regression that of the 6-month growth rate of the coincident economic index on the left-hand side. And on the right-hand side, we add the coincident economic index and also the factor from the leading variables. And then the prediction of this coincident economic index would be our leading economic index. And this is the plot of the estimated leading economic index. So on the left, we can compare with the Philadelphia Fed. So this is the sample ends in 2020. And on the right, this is a full sample where the Philadelphia Fed, at the end, they they don't have anything while we can still produce our index. And we see that in the subsample analysis that our indices are actually quite comparable. So there are some differences, but overall they capture the similar dynamics. And for the after COVID, we see a huge dip, but we also see quite quickly the factor bounces back, and it has a positive growth after July of 2020. Okay, so this is the indices constructed from the model-based approach. Alternatively, we can construct indices not without any model. We can just take the average of the series and produce some indices, and this is actually what the conference board does. They also produce this coincident and leading economic indices, but it does not require any model and just based on the weighted average of the series. And typically, the coincident economic index and leading economic index, they're expected to move together, co-move, except to the moments close to the turning points, where the leading economic index would be signaling recession, while the coincident economic index would be a bit lagging behind. However, when we looked at the official TCB leading economic index and coincident economic index, we see that throughout the sample, they have been moving quite a lot. However, at the end of the sample after 2022, we see a divergent pattern. So the leading economic index has been going down. It's been saying us already for 4 years that we are in the recession, and the coincident economic index is still trending upward. And these indices, they typically receive quite a lot of media attention, so people actually do discuss a lot what's going on here. And when we applied our model, we were quite surprised actually to see that our model doesn't have this puzzling dynamics. So we call it TCB puzzle resolved. So in our case, we see that the estimated coincident index goes up, but also the leading economic index after the COVID, it was going down a bit, but afterwards it started going again upward. And first I thought, okay, this would be maybe like due to the robustness, but actually this is more of a case that we model also that idiosyncratic component dynamically. So we include the lags in the idiosyncratic component. And actually that's a good message that the model, like actually, if you model all the dynamic properties properly, you would get less counterintuitive results, and you need to actually select carefully the model and account all the dynamic features into account. Okay, so let me conclude. So in this paper, we introduced a new class of model. We call it extended score-driven dynamic factor model. And it bridges the gap between score-driven approach and parameter-driven models. And it also allows us to model time-varying volatility and have heavy-tailed innovations. So we see that the data favors this ESDT specification with the conditional heteroscedasticity, with more emphasis actually on having the heavy-tailed innovations. And we show how to recover coincident and leading economic indices produced by Philadelphia Fed and by the conference board. Thank you very much.
Thanks a lot. Thanks a lot, Mariia. So the discussion will be given by Dalibor Stevanovic from the Université du Québec à Montréal. Can you hear us, Dalibor? We can see you now.
Now you see me. Do you hear me?
We can hear you perfectly.
Okay, now you see me. Okay, do you hear me? Thanks.
Yeah.
Okay, thanks for the organizers for inviting me. Well, thanks for the organizers for this discussion. Unfortunately, I wasn't able to for this discussion. Unfortunately, I wasn't able to come. At least share some thoughts about this paper. At least share some thoughts about this paper. So, do you see my slides now?
Strange. It's because we are listening to the echo. Yeah, now we can see the slides. Can you see?
Okay, you did.
Can you see the timer? You can't see the timer, right?
Okay, you did. Yeah. Well, I mean, so how much time do I have? Yeah. Well, I mean, so how much time do I have?
10 minutes.
10 minutes, good. 10 minutes, good. Do you hear me well? Because if you hear me twice, then do you hear me well? Because if you hear me twice, then it's a problem. No?
Hear you twice, yes.
Okay, so then maybe I should. So let me. So let me do the following. So now I will not hear you, okay? Okay. So yeah, it's a very interesting paper. So let me summarize it here first. So the problem is the following. So since COVID, well, we had extreme observations in many macro financial variables, and so it was a problem for a standard leading indicator, such as the one at the Philly Fed or the New York Fed nowcast of the GDP, because they heavily loaded on historical values of different macro variables through the standard dynamic factor model. And when you have these extreme observations, well, then this will give you quite strange factors, and by the end of the day, quite strange leading indicators. So what paper is trying to do is to propose a method which they call extended score-driven DFM, which is a bridge between the standard classical dynamic factor model, what they call parameter-driven, and the observational one, the score-driven, and in fact they combine together. So the main idea is to add this contemporaneous score to the factor dynamics. So now the factors are no longer predetermined. And then what's nice is that this under Gaussianity, at least, this nests both standard DFM and the score-driven DFM in special cases. And on the top of that, they also study heavy tails by allowing student T innovations and gauge volatility. And then the empirical results show that this helps a lot to reconstruct Philly Fed coincident leading indices, and it also helps within the forecasting. So this is just the illustrative example from the paper. So first you have this measurement equation, which is standard for a factor model, and then you have to model the factor dynamics. So the standard case is on left, this one here, when you have this measurement error or structural error on factors, and then the score-driven one is in the middle, where you have this score but at time t, not at t+1, which makes those factors predetermined. And then on the right, you have the proposal of the paper, which is to add the score at t+1, which will then make model more reliable in real time. So the first concerns non-Gaussianity, since this is one of the selling points of the paper. Well, in this particular case, it's quite tough for a reader to disentangle what is the, let's say, structural non-Gaussianity from the COVID outliers. Okay, so on the left here, you see what I mean by structural non-Gaussianity. So I'm thinking of this literature started by Lane, Saikonen, and Guerriero et al. About non-Gaussian SVRs. So that means that you have that this non-Gaussianity, in this particular case heavy tails, this is a permanent or structural feature of data, which is often the case, at least in financial series, but also in some macro data as well. And then one of the solutions proposed in the literature, at least the parametric one, is to use the t distribution throughout the sample and estimate the models with MLE or pseudo-MLE. Then you have also the non-parametric alternative. I mean, you have several of them, but let's only state this one here. So when you depart from Gaussianity, well, then you can also estimate factor models by independent component analysis. And here I just cite one paper by Bonhomme and Robert. And then on the opposite, I mean, you could have what you think is non-Gaussianity. In fact, is just presence of outliers. And now, for some people, COVID is an example of this one-time unprecedented shock that affects all series simultaneously. I mean, this is really a big shock. I mean, for the first time, at least in macro, we had a big exogenous shock, and it was COVID. So compared to the structural non-Gaussianity, so here this is not a draw from a fat-tailed DGP. It's just, you know, it's a completely different regime. So what were solutions for that, at least since COVID? Well, you can treat 2020 as missing data. You can adapt a factor model by allowing for COVID factor, like in Stock and Watson Brookings paper, or you can adjust stochastic volatility, you know, to take care of these large shocks, as has been proposed by Carriero et al. in 2024. So why this matters for the paper? Well, I mean, you have to take a stand whether this is going to deal with one-time outlier, or you want to assume that this is a structural feature of data. So of course, what they do in the paper, well, this student weight that affects all the large observations equally in the sample, so not only the COVID, but also the 2008 recession, 1980 Volcker shock, and so on. Now, one way to deal with it is also to have a time-varying volatility, which they do. But then the question is, you know, when you mix both gauge and fat tails using student distribution, which one is the most important? So the suggestion will be to compare what happens if you have this extended score-driven normal model with gauge on the full sample versus extended score-driven student with gauge, and see who wins, and then see whether it's a fat tail distribution that helps, or it's a conditional heteroscedasticity. Now, non-Gaussianity is not only kurtosis, it's also skewness, and skewness, especially in macro data, I think it's even more present than kurtosis. So think of recessions that are usually sharp, while the recoveries are gradual, which will naturally bring some skewness in real activity measures. For financial variables, this has been, of course, documented quite often. And recently, in a paper with Alain Gay, so we propose a method to deal with the non-Gaussianity in structural VARs. But we have we revisited few applications, and if you look at, for example, in the fiscal SVAR of Blanchard and Perotti, well, then you do find significant skewness in the structural shocks. And when you look at the macro-financial VAR of Gilchrist and Zakrzajsek, you also find skewness and kurtosis in this particular application. So that's maybe I mean, it would be nice if authors could add, you know, this feature. So maybe considering a skewed T distribution in place of the symmetric one, and then that will allow the score to respond asymmetrically to positive or negative shocks. So that will be one way to go. Then, of course, this is a classical factor model, so that means n fixed, and I mean, not only n fixed, n being the number of variables in the measurement equation, but it also means a small n for scalability, and then these days, at least since Stock and Watson papers at the beginning of 2000, we use those factor models more in cases where n is large. Of course, this is, you know, when you want to estimate this by maximum likelihood, it's a mess. Even though there has been some propositions, but still. So it would be nice, you know, at least to think about how to extend this procedure to a large n case. So one proposition could be, well, do a PCA on loadings, and then do extended score-driven model for the factor dynamics only. And there have been papers by now I forgot the names. It was Lucrezia Reiklin and co-authors, comparing this particular setup in the case of the standard factor model, but I think that the idea could apply here as well. And on the same time, the fragility of a small n, you have a small amount of variables, and when you have these big shocks, well, this is going to affect much more the estimation of the factors compared to a case where you have a big n. And one potential problem is, can COVID artificially generate a particular factor structure? And this echoes, these papers by Onatsky and Wang on the spurious factor analysis. And finally, the final comment, one potential application that came to my mind is measuring uncertainty, as in Jurado, Ludvigson, and Eng paper. So this is a paper in AER when they proposed this macroeconomic uncertainty measure. So the idea is to forecast a large number of time series using a factor model. So factors has to be estimated from a large panel. They do it by PCA, and then the uncertainty is constructed as common volatility of forecast errors. Now, the COVID was a big problem for this measure, and Jurado, Ludvigson, and Eng, they stopped as well to produce this measure during COVID. Why? Because when you have these extreme observations, well, then you have distorted factors, and then you get distorted forecast errors, and then you might get artificial spikes in uncertainty. And at the same time, we were also, with my colleague Kevin Morin and the student Adam Touré, we were constructing a similar indicator for Canada. So we were trying to produce this macroeconomic uncertainty for Canada during COVID, and then we faced the same problem. Then I discussed with Serena a few times, and they proposed this mean shift adjustment, which was, at least in real time, let's say, a way to adjust factors extraction. But this is, of course, not the optimal way to do. But this is just to tell you that what the authors propose in the paper could be maybe a good application for the macroeconomic uncertainty. So that will be a nice application. Of course, to do that, they have to deal with the large N. And that brings us back to the previous comment. So I'm out of time, so I will stop here.
Thank you very much, Dalibor. I'm not sure whether you can hear us again, but in any case, Mariia, please go ahead and replying.
I do. Now I do. I can hear.
Okay, perfect. Yeah, thank you very much for your comments. I think the first comment we have addressed, so this was also in the presentation. It was because it was also before asked by someone else, and then we also decided to highlight a bit more whether the Garch effect or the student T effect matters, where actually the gains are coming from. I fully agree that it would be nice to have a large N extension, especially, yeah, we have been in this conference and discussed a lot of applications where it matters. So we first thought it's important to fix this gap between and understand actually, okay, how we can bridge the gap between these two classes of models, and later on maybe also have a generalization to the large dimensional case, and then we can indeed look into the comment 4 and see how it also works. And actually, it's interesting in the large dimensional setting whether this averaging out effect would help a lot. And okay, in comment 4, you already say that in some applications it definitely doesn't help fully, but maybe in some applications I would guess that because of having a large dimensional and averaging out would also help and have less problems maybe with COVID period. But I think it's a different paper and a different research question, and how to do this as well. And I think it's also a valid point about the skewness. I think it's also worth checking and looking into this. Thank you.
Thank you very much. Then we can give the word to the AI agent again.
Given the emphasis on heavy tails and time-varying volatility, how would you recommend using ESD DFMs for real-time risk assessment, for example, the, recession probabilities or tail forecasts in the euro area, and what additional validation would you see as necessary before integrating them into the policy toolkit?
That's a good question. The AI definitely has always the toughest questions. I think like the forecasts will always come for free from this model because the model is actually aimed to be a predictive model. And then on the tail distribution, you can just take the quantile of the predictive distribution. For the recession forecasting, I think I do not see it immediately. Maybe like I think you need to think a bit more about this, but that would be also interesting. Yeah.
Okay, then are there any questions from the audience? Yeah,
So with your model, is it also possible to make longer horizon forecasts? And maybe for this application not, but maybe in an application it could be interesting in something to do something like that. And what would you do then with those scores? How do you adjust your model?
So I think for the answer immediately, right? Okay. It will be just you will be rolling the prediction step like several steps ahead, and probably that you will not have the update step. Only kind of the prediction step would matter.
Any more questions? Yeah, Lucas, please.
So thank you for the presentation, very nice. At the moment, the model is used to solve a filtering problem, so to filter out the leading economic index. At the same time, it would also be interesting to use the model for out-of-sample forecasting, and in particular out-of-sample density forecasting, because now the point predictions are the same, but the extended score-driven model has this additional term for the variance of the predictive density. So the tail forecasts would be different, and that would be interesting to explore. So my question is, have you thought about in this direction?
So we didn't do this in the empirical application, but we looked into this in the Monte Carlo application simulations. So we simulated different processes, and we looked at both the point forecast at the mean squared error, but also at the logarithmic scoring rule that would actually summarize how well you predict the density. And there we see quite a lot of gains, and we actually do improve a lot upon the standard models. And also not necessarily in the student case, also in the Gaussian case could be some improvements, because as I said, we nest the parameter-driven model and the score-driven model. So it also means that we can do better even in the Gaussian case, not necessarily in the student case.
I would have a small question. In the first volatility factor picture you showed, I think, the spike was COVID clearly, but then the 2 or 3 other large spikes were in the 90s, and that was what I found a bit surprising. I would have expected them in the 70s, or where the economy was more volatile. Is there any intuition for that result? I mean, the differences were not big, but it just caught my eye.
I think it's like here the COVID really like dominates the whole picture. I think if you zoom in, you can see a little bit of the grade moderation there period. And I think some series are just also noisy, and sometimes kind of this volatility captures kind of some series are like having this extra noise that sometimes kind of you can attribute to something like grade moderation, like in the 80s, but sometimes, yeah, also I think not all the periods are like fully interpretable.
Okay, thank you. Oh yeah, there's another question by Gerhard.
Yeah, just for curiosity, we actually have some score-driven model running here that models time variation and skewness of the distribution. Yeah, could you combine this, integrate this into your factor model, having time varying skewness in No, actually, it's a stupid question. Sorry. Doesn't work.
Why?
Because you don't have an innovation for the factor. You don't have an innovation for the factor.
So now we actually do have innovations, but it's the same as in the measurement equation, right? I don't have an immediate answer about the skewness, so that's why I also can't say that the question is. But yeah, I think it may be interesting.
And there's a question from Malte.
You mentioned briefly this change in the approach of the New York Fed, and you sort of alluded that yours might be more attractive for computational reasons. So I was wondering whether you did this kind of comparison and how this might depend on the size of your data set and also how it might affect the actual indicators.
Yeah, so in the New York Fed, I think they do it for nowcasting, so this is not a focus of this paper, and they also have a bit more like the large N problem that we actually like with our estimator, because we want to estimate everything with maximum likelihood, so we don't want to have too many parameters to estimate. So some options where you can maybe indeed take out the loadings, you estimate them first somehow, like using PCA or some other method, and then run our model would be more computationally attractive, let's say. So that's why we didn't compare to the New York Fed, but only focused on the construction, composite, and leading indices.
Okay, thank you. If there are no more questions, then let's thank Mariia and Dalibor again for the excellent presentation and discussion.